Hello teachers, welcome back to section 12-4. Now in 12-4 in part 1, we spent a lot of time talking about congruent figures versus similar figures. We talked about the definition of similarity and how you could prove triangles are similar using side, 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 and angle, angle. We also talked about dividing a triangle up using parallel lines and equal segments that are proportional, and we talked about the mid segment. That was the last thing we discussed in the video, and we're going to use that mid segment idea for this problem. So this video is mainly about problems in section 12-4. So here we go. We have in quadrilateral ABCD, you see clearly we have four sides, so it's a quadrilateral. M, N, P, and Q are the midpoints of the sides. So again, M is the midpoint of AB, N is the midpoint of BC, P is the midpoint of CD, and Q is the midpoint of DA or AD. All right, what kind of quadrilateral is MNPQ? Okay, now, first of all, MNPQ, what is that? That's the guy inside. That's the blue guy, right? MNPQ. If I highlighted it, it looks like my highlighter is not set. I promise I set it. MNPQ. There we go. That's what we're asking. What kind of quadrilateral is that? You're not allowed to just look at it and decide. You have to prove it, just like everything else in this course, right? You got to have some backup. So let's see what we can do with this problem. Okay, now very important that it said that M, N, P, and Q are midpoints. So let's focus on N and P right here. Now, how about, you see that the dashed, the diagonal between B and D, that's a diagonal of our quadrilateral. Let's just focus on the triangle on the right side of that diagonal, which means we can use our mid-segment rule. Let's go back and look at that. All right, so what does it say? That if M and N, okay, are mid-segments, so M is the midpoint of AB and N is the midpoint of BC, then we can say MN is parallel to AC. I wonder if we can use that. Let's go back, okay? So again, we know that N is the midpoint of BC and P is the midpoint of CD. Not only that, we know that because it's noted. Look, this is the two lines and the two lines, which means these two segments are congruent with the 3 and the 3. That means these two segments are congruent. So you know what I know now? I know that NP, okay, so let's write line segment NP is parallel, what's it parallel to? How about BD? Fair enough? Now, that's because, again, of the mid-segment situation, okay? NP is a mid-segment. Mid-segment. How about mid-segment? There we go. Whew! All right. Now, here's what I want you to do. I want you to also take a look at the left side triangle right here. There we go. Now, we also know that M is the midpoint of AB. It told us that. Not only that, look, this is one mark. That means that AM and BM are congruent. Same thing over here with the 4 and the 4. That means that AQ and DQ are congruent. It also means that line segment MQ is parallel to what? The base of that triangle, which is BD. Once again, by the mid-segment, not mid-segment. There we go. Mid-segment rule. Okay? Now, how does that help us at all? Well, you know what? If NP is parallel to BD and MQ, I can't read my writing, is parallel to BD, hey, can we not say that NP is parallel to BD? Okay, so NP right here is parallel to, I wrote the wrong thing. It's not what we're trying to do. We already have that written down. How about NP, what am I trying to say, is parallel to MQ? Right? Do you buy that? Sure you do. Now, what am I aiming at? I'm trying to figure out what kind of quadrilateral this thing is, because if two of them are parallel, that means I might have a trapezoid. But now we have opposing sides are parallel. Well, one pair of opposing sides are parallel. You think we could prove the other pair of opposing sides are parallel? So hold that thought. I've got this typed up. I'm writing a whole bunch of stuff, but I have it typed up, so let's recap. Okay, so NP is the mid-segment of triangle BCT, so NP is parallel to BD. That's the first thing we did, right? Next line says MQ is a mid-segment in triangle BAD. Hey, I didn't notice that. So triangle BAD, that guy right there, because that's a mid-segment, then we can say MQ is parallel to BD. You know what the next line's going to say? You should, right? Because we just did this. Therefore, MQ is parallel to NP. So again, here we are. MQ, I'm trying to highlight it. MQ is parallel to NP. Now again, the argument, can we do this the other way? Okay. Now, here's what the book says. Similarly, we can show that MN is parallel to QP. Are you buying that similarly stuff? I tend not to like to use the similarly stuff. I want to jump in there all the way. So, what if we put a diagonal right through here, okay? And let's just take a look at this triangle, just to make sure you're really following what's going on, okay? Now, we know that M right here is the midpoint of line segment AB, and we know N is the midpoint of line segment BC. How do we know that? Well, I think they told us that in the beginning. But it shows it in the diagram because this is marked 1 and this is marked 1. They're the same length, therefore that's right in the middle. Same thing with the 2 mark and the 2 mark right in the middle. So what does that mean? That means that MN is again a mid-segment. I have to watch how I write that and say that. Okay, so MN is a mid-segment. What does that mean? That means MN is parallel to the base of that triangle, which is AC, line segment AC. All right, now let's use a different color highlighter because you know I love to do that. All right, so here we go. We've got our triangle over here to the right, and there's the base of that triangle. Once again, similar argument, right? But I don't like saying that. Over here, Q. Do you agree that Q is the midpoint of line segment AD? Well, absolutely, because that's a 4 and that's a 4, so it's right there in the middle. Do you also agree that P is the midpoint of line segment CD? Yes, because that's marked 3 and that's marked 3, so they are congruent line segments. What does that mean? That means that line segment QP is a mid-segment. Well, how does that help out at all? Well, if QP is a mid-segment, then we can say that our mid-segment, QP, is parallel to the base of our triangle, which is AC. Now, if we go back and look at what we have here, we know that MN is parallel to AC and QP is parallel to AC. Well, the final outcome here is that MN is also parallel to QP. So now our mid-segments are parallel to each other. Now, what does that mean? That means this guy right here is parallel to this guy right here. And we had already shown, not highlighted anymore, that this guy right here is parallel to this guy right here. What does that mean our figure is? Please don't say anything but a parallelogram. I'm struggling to write. There's a big old delay between me writing and the actual marking coming up, so it's confusing. Sorry about that. All right, so final outcome, boom, there it is. MNPQ is a parallelogram. It's a great problem. It's not a hard problem, but you really want to be able to explain every single thing you're doing, and I like that problem for that very reason. So I have a definition for you here. Okay, a median of a triangle is a segment connecting a vertex of a triangle to the midpoint of the opposite side. So let's focus on vertex B. So we are just going from that. Now this is not an angle bisector, okay? This is also not a perpendicular line, which is an altitude. This is the medium, okay? So what this is a segment bisector. We're dividing the side across from our vertex or our angle into congruent parts. That means that AN and NC are the same length. Okay? That's called a median. All right? Now, there's a median coming out of A as well, and then A comes to M, which means the length from BM is the same as the length from C to M. All right? And then coming out of vertex C, I draw a median which divides the line segment BA into BP and AP. All right, now notice what happens. They intersect in the same point, which is very cool. So the three medians are concurrent. That's when you have like three lines that are going towards each other or running into each other or intersect. The point of intersection, G, okay, is called the center of gravity or the centroid. So those words are used, or names are used interchangeably. I've heard centroid a lot, of the triangle, okay? The centroid of a triangle divides each median in the ratio 1 to 2. Okay, this is without proof, but it's pretty cool. What do I mean by that? Okay, so this length, let's look at our first one, B. If this were length 1, then this is length 2. Okay, or if this were 5, then this would be 10. You get the point? So the longer one is twice as long as the shorter one, and that's true for all of those. Okay, so again, if this were 1, this would be 2. If this were 1, this would be 2, or twice as many. So it turns out similar triangles have long been used to make indirect measurements. So we can determine the height of the pyramid using similar triangles. How does this work? Well, here we go. All right, so the similar triangle is this triangle drawn. Notice we have a shadow length. So we could measure that shadow length. And we also know how tall this person is. So again, this is this person's shadow. So let's say the shadow was 9 feet and this was a 6 foot tall person. Well, at the same time of day, right, you want to do it at the same time of day, you could get the shadow of your pyramid, and using this as a proportion, so we write the ratio for this situation, and you write the ratio for this situation, we could calculate the height of that pyramid. Okay, and don't worry, I have an example for you. Okay, so here's the information we have here. On a sunny day, a tall tree casts a 40-meter shadow. Okay, so there's our tall tree. It casts a 40-meter shadow. All right, the goal is to find out how tall the tree is. At the same time, notice that's important, because if you do this a different time of day, your shadow is going to be different and it's not going to be proportional. So at the same time, a meter stick held vertically casts a 2.5 meter shadow. So you have just a meter stick, and it casts a 2.5 meter shadow. How tall is the tree? You know what? We can set up proportion triangles here. All right, so how about I do this? Let's set up the ratio here. So I could say that this 1 meter here compares to what part of my other triangle? Well, that's the x, right? So 1 meter over x meters, okay, is equal to, now, let's pick proportional parts here. How about 2.5 meters? Remember, we put the smaller triangle on top, so the larger triangle information is on the bottom. I have to be consistent. Smaller triangle on top, and then larger triangle 40 meters on the bottom. Now, notice all the units are the same, so let's just not worry over meters right now, okay? That means our answer is going to be in meters. How am I going to solve this problem? you know the drill. You cross multiply. So when you have a proportion, we can cross numerator to denominator. So I have 1 times 40 is equal to, again, numerator times denominator, 2.5 times x. Well, 1 times 40 is 40 equals 2.5x. Now, you know, our properties of equality allow us to divide on both sides. So to get this x isolated, I'm going to divide both sides by 2.5. And we know that, or we could type it in our calculator, that 40 divided by 2.5 is 16. Now, we know better than just to circle our answer right here. We would say the tree is 16 meters tall. And always try to answer your problems in sentence form. It's probably something I should work on as well. I have the typed up version of this. Okay, so the triangles are similar, so x over 40 is equal to whatever 2.5. Now, if you remember the way we did it, I set up the proportion the other way. They put the larger triangle in the numerator position. Actually, they didn't do that at all. They did x over 40 equals 1 over 2.5. Is that okay? Well, we talked about that when we covered proportions. There are 4 different ways to set up your proportion, so that is okay. The reason I did it the way that I did is because that's how we had to set up the scale factor when we were working with similar triangles, and so I wanted to be very consistent about that. But notice the answer is the same. We got 16, so that's perfectly fine the way they did it. All right, so I've got a homework example for you, and hopefully this will help you when you run into a similar problem from your homework. So we've got triangle ABC is similar, hey, that's important, is similar to triangle DEF with a side of triangle ABC that is 81% of its corresponding side in triangle DEF. Also, triangle GHI is similar to triangle DEF with a side of triangle GHI that is, I know you can read all this, 29% of its corresponding side in triangle DEF. Whew, that's a lot. Now, they're asking if they're similar to each other. Why or why not? Let's address that. And what is the ratio of correspondence of sides of triangle ABC and triangle GHI? So let's try to break down this information into something that makes a little bit more sense and doesn't run together. So triangle ABC is similar to triangle DEF. Let's write that down. So we've got triangle ABC is similar to triangle DEF. Now, that alone means all the angles are congruent, which means they're the same measure, and all the sides are proportional, which means there's a scale factor to get from one triangle to the other triangle, okay? Now, that scale factor is given to us. It says triangle ABC that is 81% of its corresponding side of DEF. So this gives me the impression that ABC, triangle ABC, is smaller than DEF because one of the sides is 81% of the corresponding on the triangle DEF. Now, because they're similar, that actually is true for all of the corresponding sides, not just one of the corresponding sides. Okay? Now, I want to be able to write these sides as equal to each other. So how can I do this? I could say that it's 81, ABC is the smaller one. Okay, so 81% of triangle DEF equals triangle ABC when you're just talking about corresponding sides. So I'm going to write something that looks a little weird, but it's going to be 81% of triangle DEF. I'm just going to put DEF, and I'm really talking about the side lengths, is equal to ABC. Okay? And really, again, I'm not saying you can take 81% of DEF because DEF defines a triangle. What I'm talking about is 81% of the side DE, 81% of the side EF, and 81% of the side DF. Okay? And that will give us the smaller triangle ABC. Make pretty good sense. You with me? Okay, let's keep reading. Also, triangle GHI, let me highlight that. GHI is similar to triangle DEF. Okay, now how do I write that? So triangle GHI is similar to triangle DEF. Okay. And then it says that, playing with pens, it says that triangle GHI that is 29% of its corresponding side in triangle DEF. So we have, again, a side of GHI that is 29% of the corresponding side in DEF. So again, GHI is smaller. To equal GHI, I would have to take 29% of DEF. Okay, so I'm going to write that down, that 29% of DEF is equal to GHI. Okay, so we've got all that information written down. Now, let's read our question. Are ABC and GHI, so ABC is over here, so this one, and GHI over here, are they similar? What do you think? Okay, well, again, if there is a scale factor between each of the lengths of ABC, so we're talking AB, BC, and AC, if I can multiply that by something to get to GHI, then they are similar. We already know they have the same angles, right? How do we know they have the same angles? Well, because they're similar. Matter of fact, we could say they're similar. Really, we could say they're similar because of angle is what I argue, without even considering the sides, because if ABC is similar to DEF, then they have the same angle measure. And GHI is similar to DEF, they have the same angle measure. So ABC has the same angle measure as GHI. Done with that question. That's how I would argue that. But B, we need to know the ratio of corresponding sides of triangle ABC and GHI. Now, our only link between ABC and GHI is DEF. Okay, so I know that 81% of DEF is equal to ABC. Now, dealing with percents can be kind of a pain. So you know what I'm going to do? I'm going to change that to a fraction. Okay, because scale factors were typically in fraction form and not percent form. All right, so 81%, you know the definition percent, that means 81 out of 100 times DEF is equal to ABC. Okay, over here we know 29 out of 100 of any of those sides, DEF, is equal to GHI. Okay, now again, our connector is DEF. You know what I want to do? I want to solve for DEF. I want to get DEF all by itself. Now, if you were looking at the textbook version of this explanation, they're really not going to write DEF. They're just going to pick one of those sides, like DE, okay, and one of these sides, like DE, and one of these sides, like AB, and one of these sides, like GH. That is really a much more appropriate thing to write. So, you know what? That's what I'm going to start writing now. Okay, so let's solve for side DE. Let's get it by itself. How am I going to do that? Well, I'm going to get rid of this 81 over 100, right? I'm going to multiply this side by 100 over 81, and I'm going to multiply this side by 100 over 81. So now we have the fraction that side DE is equal to 100 over 81 times side AB. Okay? Very similar thing on the other side over here. To get the DE by itself, I'm going to multiply by 100 over 29 over here and 100 over 29 over here. The reciprocal, right? That's what's going to get rid of multiplication. So because the 100s cancel, the 29s cancel. So now I have that side DE is equal to 129ths side GH. Now, why did I do that? Because look, these are the same. So if D equals 100 over 81 AB and DE equals 100 over 29 GH, can't I just set those equal to each other? Okay, so 100 over 81 AB is equal to 100 over 29 GH. Now, what am I going to do next? Well, Miss Wilson, you're going to add another page because you're running out of room. So, hold on. That's what I'm going to do. So, this is where we are. Now, I've got to solve for either line segment AB or line segment GH. Notice it says what is the ratio of corresponding sides of ABC and GHI. So what I'm going to do is I'm going to get the AB segment by itself, so I can say that that scale, if you take AB and you multiply it by this scale factor, you will get GH. So let's solve for AB. So how am I going to do that? I'm going to multiply this side by 81 over 100 and this side also by 81 over 100. So that's going to give me line segment AB or any of the others. Okay, there's two others we could choose. And notice if I ignore the GH for a minute, I can cancel 100 and 100 here. So I get 81 over 29 times GH. In other words, that is my scale factor. Any side of AB, if I multiply it by 81 over 29, I get GH. It doesn't ask for this in terms of percent. It just wants to know the ratio that you should multiply to get from one to the other. Okay, I hope that helped you out when you get to a problem like that, and I've got a similar one coming up. So if you copy a document on a machine, you should get a similar copy. So you remember we're talking about similar and similarity in this section. Suppose you want to reduce a document to 1/5 of its original size, and you first reduce it by 25%. We want to know by what percent, so this time it asks for percent. By what percent do you need to reduce the copy to obtain the desirable size? Now, I think it's worth pausing and really investigating this so you could potentially run into some of the issues that I ran into. But in case you're just going to hang with me, let's talk about it. All right, so if you copy a document on a machine, you should get a similar copy. Suppose you want to reduce a document to 1/5 of its size. Okay, so we in the end, we want 1/5 of its size. So I could write that as my goal is 1/5 of X. That's my ultimate goal. Okay, whatever the size is. All right, now we started off by reducing it by 25%. So is that 25% of X? So my first thought that it was, but you know what? This is why I'm showing you this problem, by the way. If you reduce it by 25%, that means you removed 25%. What is still sitting there, y'all, if you remove something 25%, what's left? How about 75% is remaining? So the size now is 75% of the document, okay? So let's write this down. So this is the goal, but right now we have 75% of X. And we want it to be 1/5. This is what we're going for, 1/5 of X. Okay, now one's a fraction and one's a percent. You want to get rid of that situation? We can, or we can write 75% as a decimal, but I don't want to leave the percent sign in there as calculation. So one way we could go with this is say 75 over 100 is what we've got now. Okay, now we need to multiply that by some factor that we don't know yet that's going to equal 1/5 of X. Notice it didn't say reduce it. Suppose you want to reduce a document to 1/5, not by 1/5, but to 1/5. Yet you reduced it by 25%. And again, that's what hung me up to start with when I first started doing this problem. So reduce means you get rid of that much. Just like when something's 20% off, that doesn't mean you pay 20% of it. It means you pay 80% of it, right? Anyway. All right, so now to do this problem, the X's are on both sides, so I'm not going to be concerned with the X. I'm going to be concerned with my variable here, which is question mark. Okay, so let's write it this way. So 75 over 100, by the way, is 3/4. Am I right? Okay, so I could say 3/4 times something, let's call it Y, that's my question mark, is equal to 1/5. That's really what I have going on. I need to know what 3/4 of what is my new document, what I'm going to have to reduce by. Now, we haven't done the reduce yet. I just need to know what size my document has to be of its original or of its 3/4 sides to get the 1/5. So I'm going to solve this equation. You know how I'm going to do it. I'm going to multiply both sides by 4/3. The reciprocal. Okay, so that's a property of equality. The 3's cancel, the 4's cancel. Now y is all by itself coming up here, so y is equal to, when I multiply on this side, that's 4/15. Okay, so that is the next run through of the copier. So 4/15 of the size that is now. Okay, but now that's not the reduced size. All right, now we can change 4/15 to a percent by changing 4/15 to a decimal. Okay, so let's do that. So 4/15 as a decimal, that's 4 divided by 15, which results in y, is my pen working? Y is equal to 0.2666, and at the end of that, there's a 7. Now, how do I change that to a percent? 2 places to the right, you agree? So that would be y is equal to 26 and that really is a 6 repeating. You see that? Now that's a percent. When you move the decimal 2 places to the right or multiply by 100. Now that's not the reduce. That's the as is. So if we had 75% of the size originally and then we multiply it by another 26.6%, that's going to give me 1/5. But what do I reduce it by? Well, reduce, remember, is the opposite percent. So if I take my 100% and I subtract my 26 2/3%, where did I get that from? Remember, 0.6 repeating is 2/3. That's going to give me, just subtract it, 100 minus 26 2/3 is going to give me 73 1/3%. That's what they want here. 73 1/3%. So again, the confusing part comes in, and I may have confused you more. It wasn't my intention. But the outcome is 1/5 of its original size. But when you run it through the copier, okay, then you have a reduced amount, not like a is amount, like it's going to be 25% of its original size. No, we're going to reduce it by 25%, which means it's going to be 75% of its original size. And so I worked with that. Now, there are probably other ways to handle it. This made the most sense to me. You might be thinking, why didn't you just, hey, if it works, I'm all for it. Okay, but I just wanted to explain it the way that it made good sense to me, and hopefully you'll get through that problem also. This is the end of section 12-4. It's the end of chapter 12 also. So if you're struggling, please let me know, and I hope you have a great day. Reach out if you need it.